Hey everyone, welcome back. So in this video, I want to go over the gravitational potential energy, but from the perspective of chapter 13, right, with universal gravitation in mind. Up until now, we've only talked about potential energy in terms of MGH, right? Way back in chapters 7 and 8 when we originally talked about conservation of energy. So take, for example, you have, say, the ground on the surface of Earth, and some object, it doesn't matter what it is moved from, say, some initial point, which we'll call the ground, right, which has an initial potential energy of UI, at a height h equals 0, sure. And if it goes up some height h, well, it's going to have a final potential energy, which we said was at some, height h. The form of U back in chapter 8 was mgh, right? So actually what I should put is those in the other order. So I should put this is at some height h, this is at some height 0. And so the final potential energy had the form of mgh, right? And at the bottom, mgh was just 0 because the height was 0, right? So what I didn't tell you back in chapter 8 was that we could only do this for a very certain reason. And that reason was that the force of gravity, which we called mg back then, was constant. Okay? And it was constant back then because we didn't really go too far away from Earth. Right? We pretty much stayed near the center. Okay? So the force of gravity was a constant mass times gravity, mg. Now in chapter 13, we're taking a look at gravitation in general, right? In any possible configuration, right? Any possible distance between two objects. So that means if we take a look at, say, a planet of some radius and some mass, right? Now, if some spacecraft, for example, were to launch from the surface, so it starts there, we'll say it has an initial distance of pretty much the radius of that planet, and then it's launched and it goes all the way up, keep going, and well, really, let's take this all the way to its conclusion, and we'll say, what if it goes to an infinite distance away, right? Like the Voyager spacecraft. The Voyager spacecraft is well past the orbit of Pluto. In fact, it's well into the Kuiper Belt. It's billions and billions, if not a trillion miles away from Earth. It's been going since, I think, 1971, 1972. It's been going a long time, and it's a very far distance away. So eventually, if it doesn't run close to any other massive objects, that'll be an infinite distance away. So let's take a look at what its gravitational potential energy would be. This differs from chapter 8 in that now, at these great distances, the force of gravity, way out here, is not constant. Okay? Not constant because we're at a substantial distance away. Remember, the force of gravity is a field force. And so because objects are such a great distance from the center here, right? Much further than just the radius of the Earth, the force of gravity continuously decreases as 1 over the distance squared. So let's take a look at the forces on this object and how that relates to now its gravitational potential energy in the general sense. So if it's moving outwards, we can call that its dr, right? The differential displacement. There's a force back towards Earth. There's an attractive force on it, and we'll say that's the only force. Okay? So, if that's the only force, I want to ask what the work done by the gravitational force is. Right? What's the work done? Well, if it's still moving out, they're in opposite directions, so hopefully we get a negative work. So let's see. Integral F dot dr, right? That's always work. In this case, the force is the force of gravity, and that has a magnitude we now know as Gmm over r squared. R being whatever distance it is from the center, right? The center of mass of that object to the center of mass of the planet. And dr has just the magnitude of that integral. And now, since it's a dot product, we have to have the cosine of the angle in between. Well, that's just 180. And so that gives us, whoops, a -1. Okay. All right. Let's see. What are our limits of integration? What are we integrating from and to? Well, take, for example, this was a spacecraft. It's launched from the surface, so it starts at a distance capital R, and then after an infinite amount of time, let's say it goes an infinite distance away. So really we're integrating from R to infinity. Okay, I'm just taking the max-min cases here. So we have a negative Gmm, and we're integrating from R to infinity dr over r squared. Right? That should give us negative 1 over r. And then if we plug in the limits, well, before that we can actually cancel out those negative signs to give us Gmm over infinity minus Gmm over capital R. The first term just goes to 0, basically. And so, indeed, we're left with a negative expression for the work, right? And so, if you remember back from chapter 8, work relates to the potential energy as negative delta U, right? And this is, in fact, what we have here. So, to say this another way, the object, when it was on the surface at launch, initially, that was the closest that center of mass will be to the center of mass of the planet. So thus, the gravitational potential energy was at a minimum, right? They were closest together. And so that means that this distance on the bottom was the smallest it'll be. If the number on the bottom is smaller or goes smaller, that means overall the fraction gets bigger and bigger. But we have a minus sign in front. That means the biggest this potential energy can ever be is 0. Okay. The flip side of that, when this satellite reaches an infinite distance away, the distance on the bottom, in fact, let me go ahead and write the general case. So U is minus Gmm over just a general R, right? When R is infinity, right, this whole potential energy is 0. In other words, it's maximized. I think I said that incorrectly earlier. Let me go ahead and write it over here. So we have two cases, okay? A start and an end. So let's take a look at them both. When R goes to infinity. All right, so at the start, right here, when R equals R, the potential energy is equal to minus Gmm divided by the radius of that planet squared, okay? If it's launched from that surface of the planet, the kinetic energy, which is 1/2 mv squared, that's the maximum. Kinetic energy is maximum. That means the potential energy has to be at a minimum. And in fact, it is, right? They're the closest they will ever be. So U is at a minimum, all right? Let's see here. Kinetic energy is at a maximum. When that object that's launched from the planet reaches an infinite distance away, in theory, of course, U minus gmm over infinity, well, this is just about 0, right? Minus g, the big number, basically 0. So that means that U is actually a maximum now, which should make sense. The two objects are furthest apart. The kinetic energy, 1/2 mv squared, is now at a minimum. That object, as it's been moving away from the planet, is slowing down, right? And eventually it's basically going to be moving at, 0. Well, look at that. That means when it's at an infinite distance away, both the potential energy and the kinetic energy is 0. Let me write that a different way. V will be about 0. There we go. So take a look at this. At an infinite distance away, both the gravitational potential energy and the kinetic energy is 0. That means that the total mechanical energy of the system, and the system being the planet plus that satellite or that object of mass lowercase m, right? Final. Their sum is 0. Their sum is 0. The potential energy has a maximum value of 0. It has a minimum value of, well, it depends on the mass and radius of those objects, right? But by minimum, I mean most negative, right? From conservation of energy, the mechanical energy at launch, at the start, should also be 0. 1/2 mv squared. Now it's minus gmm over capital R. It should also be 0 because it turned out to be 0 at an infinite distance away. So let's see what that means as far as this speed here. What speed does the object have to reach an infinite distance away? That's known as the escape speed. So I'm just going to solve that equation for V. We see that the mass of that spacecraft or the satellite cancels out, and we should get 2gm over the radius of the planet square root. Okay? And so this is known as the escape speed. To put this in context of the rest of the video, it's the minimum speed an object needs to escape from a planet's gravitational pull. In real life, right, in practicality, that's impossible because gravity reaches for an infinite distance away. But just for the purposes of this chapter, we define gravitational potential energy to be 0 at an infinite distance away. That allows us to not only say, that it's 0 at an infinite distance away, but also that the total energy of the system is 0. This is a good precursor to orbits, okay? So keep this in mind when you watch that video, all right? So I hope this has given you a little bit more of an insight into what gravitational potential energy is in terms of two massive objects, okay? So with that, thanks for watching.